Okay, shall we start maybe? Yes. Okay, so before introducing our today's speaker, I just wanted to make a quick announcement. As we mentioned during our seminar last week, and as you may have noticed from our website, we'll be moving soon our imaging seminar series to SIAM, Activity Group on Imaging Science. So the web page and the invitation emails will be soon managed by SIAM. I just remind you that those of you who were already registered to our imaging mailing list will be automatically added to the SIAM list. So we are still in the process of doing this change, but we expect this to happen in the next couple of weeks. So stay tuned. Okay, so let me now move to our today's seminar. So it's my great pleasure introducing Samuli Siltanen. Samuli is a professor of industrial mathematics at the University of Helsinki in Finland. So he completed his PhD at the Helsinki University of Technology in 1999, after which he worked as an R&D scientist for 3 years. He then spent 2 years as postdoctoral fellow at the Gunma University in Japan, 1 year as R&D scientist at the General Electric Healthcare in Finland, and became professor of mathematics at Tampere University of Technology in 2006, before moving to Helsinki in 2009. Samuli's research activity is internationally well acknowledged. It focuses in particular on the design of efficient numerical methods with solid mathematical bases, solving real-world inverse problems encountered in medical imaging, such as, for instance, EIT, low-dose 3D X-ray imaging, and many more. His research activity has been awarded with several international distinctions. So here I will only mention a few. For instance, the very recent 2020 Mathematics Prize funded by the Finnish Mathematical Society, the Snellmath Prize in 2018 awarded by the University of Helsinki for his science dissemination activity, and the role of team leader of the Finnish Center of Excellence in Inverse Modeling and Imaging, funded by the Academy of Finland, whose research activities have been running now since, I guess, 2012, possibly. Samuli is also the president of the Finnish Inverse Problem Society, whose website is very rich of information on seminars, workshops, and it also contains open datasets, which are very worthwhile to look at. So I really recommend it. So today, Samuli will present his work on classifying stroke from electric data by nonlinear Fourier analysis and machine learning. Just a quick reminder to the audience, in case you have any questions, please write them using the chat button or the Q&A window, and we will read them to Samuli at the end of his talk. Okay, so with no further ado, Samuli, I pass you the stage.
Thank you, Luca, very much. And thanks to all the organizers for the honor of speaking in this distinguished seminar series. So somehow the basic message of my talk today is that now while machine learning becomes more and more useful and important for inverse problems, it may sometimes be a good idea not to learn directly from the measurements and try to reach a reconstruction or classification, but maybe it's a good idea to do some traditional inverse problems math in between in a noise robust way, and then learn from such features. So today I will discuss such an approach related to electrical impedance tomography and stroke. First, I'd like to mention, though, the Finnish Center of Excellence in Inverse Modeling and Imaging. As you see, we try to cover the map of Finland with inverse problems research groups. We are doing pretty well, I think, in that. And also, I mean, if you are into entertaining science content, please take a look at my YouTube channel. There's a lot on inverse problems too. Okay, so my talk today is organized like this. First, I tell a little bit about EIT, and then I go more into CGO solutions and this virtual hybrid edge detection methodology. So EIT first. So the basic idea in EIT is to attach electrodes to the surface of a physical conducting body, such as a patient, and then feed electric currents into the body, measure voltages, and try to make an image of what is inside. And let me also stress that the measurement is such that For example, in this phantom measurement built by John Newell, we apply many current patterns. So you see on the right-hand side, different ways of putting current into the domain and taking current out of the domain. What I'm showing are the so-called trigonometric current patterns. There are others as well, but the point is that the EIT measurement is made by applying many different current feeds and then measuring the corresponding voltages for all of those applied current patterns. And all of these measurements form an operator. So this is just one picture of a D-bar reconstruction. And the mathematical model I'm using in today's talk is two-dimensional, and it's the classical one introduced by Alberto Calderón in 1980. I restrict to the unit disk, although I mean all of this can be done in more general domains, but for simplicity, I'll work in the unit disk omega, and inside omega there is a non-negative function, strictly positive function sigma, which is the electric conductivity. I assume that it's bounded away from zero and it's also bounded from above. Usually it's like piecewise constant or something like that, but L infinity is kind of the reasonable limit in regularity. So the measurements are modeled by the so-called Dirichlet-Neumann map. So actually, for mathematical convenience here, I'm not talking about electrodes or current to voltage matrices. I stick with the more ideal mathematical measurement model, the operator that takes any voltage distribution applied at the boundary, that maps it to the current through the boundary. So we think we know this one, although in practice, of course, we only know a noisy approximation to it. But let's follow Calderón's original idea and look at what we can do with the Dirichlet-Neumann map. So let's look at the complex geometric optics solutions and the D-bar method. The results in this part of the talk are done with David Isaacson, Kim Knudsen, Matti Lassas, John Newell, and Jennifer Mueller. And here the idea is to take a look at a certain nonlinear Fourier transform, which I'm showing in brown here. It's a complex valued function in the complex plane. This is the real part. Adrian Nachman introduced the use of this transform in the 2D EIT in 1996. He showed in his seminal paper that if we know this operator, we can put it into a boundary integral equation, calculate this nonlinear Fourier transform, and then apply a nonlinear inverse Fourier transform containing a D-bar equation, and then recover the original image. It turns out that when instead of the DN map, we have the noisy measurement matrix, and we put that to an approximate boundary integral equation, what happens is that in a certain disk, we get reliably the nonlinear Fourier transform values, but outside some circle, the results are corrupted by numerical errors very badly. And then if we do the nonlinear inversion, we get a lousy image. And if we do a low pass filter here, which is of course a nonlinear operation now because the transforms are nonlinear, we will get a robust, noise robust image, which however is blurry because of the low pass filtering. We first did it with Jennifer and David in 2000, and then later more properly and proving some regularization properties of this approach in this paper. And note that these complex geometric optics solutions that were first introduced by Sylvester and Ullman in 1987, they serve a very nice purpose here for the extremely ill-posed problem of EIT, that we can divide this nonlinear frequency domain into information which is robust, and information which is sensitive to noise. So somehow we can look at the ill-posedness of the problem in this very clear way. We can divide our information into stable and unstable, and this will come up later in the talk as well. Here, just see if we have more noise. So I'm kind of adding heavier and heavier simulated noise in this computational experiment. Then you see we have to truncate more and more severely on the transform side, and then our image gets more and more blurry, exactly analogous to linear Fourier transform. And just to mention that we have a proof of regularization with a convergence rate in Banach space. So a very similar result that people usually prove using Tikhonov functional techniques, but we can also do it using functional analysis and complex analysis with a nonlinear PDE technique like this. And it's a non-iterative method, so it's nice in that way. And just to mention the medical importance of EIT, this lung imaging may be the most advanced application of EIT in medicine. These pictures are from Jennifer Muller's group from Colorado State University. And here the idea is that patients with cystic fibrosis develop a very sticky mucus in their lungs. So when they breathe, not all of the lungs are filling with air. And for small children, it's very hard to measure this because they cannot do the spirometer where you blow to a device that measures how much air you have in the lungs. But it turns out, as Jennifer showed, that you can measure even small children with EIT and get reliable estimates of the lung content. And also let me mention that this blurring of the D-bar method can be also removed by using machine learning, as Sarah and Andreas showed a few years ago. Okay, let me then turn into the main medical motivation of this talk, which is about stroke. There are two kinds of stroke, which is a problem with blood circulation in the brain. On the left here, you see so-called ischemic stroke, when this part here of the brain is not getting blood because there is some blood clot in the vein. And here, this white part is bleeding. And the symptoms are the same in both cases, but the treatments are completely opposite. For this patient, you can try to give blood thinning medication, but for this patient, you really shouldn't give that. And actually, there is no effective treatment for brain hemorrhage. But you need to know which one is which, and you need to have a method to monitor what's going on in the brain. So we are examining EIT for this purpose. It's kind of promising because inside the head, we have these different conductivity values or resistivity actually in this picture. We are thinking that maybe some measurement device like this could be used. And then according to the doctors in our team, maybe the most important application would be on the bedside monitoring in situation like this, because currently when the doctors want to know how the patient is recovering or what's the situation, they have to take the patient to a CT machine. So to detach the patient from all of this and take them to measurement. But we could have EIT machine here in real time and not affecting the situation too much. And let me also mention that we have already a second project now funded by Jane and Aatos Erkko Foundation. So now a new project with 1.3 million euros to continue our research work on this topic. So I'm describing what we do at University of Helsinki with Rashmi Murthy and also Fernando Mura, who is visiting us. Also, this is in the Kuopio group in University of Eastern Finland. We have all of these approaches to study electric imaging of the brain. Okay, so in my group, we are now examining the use of CGO solutions and machine learning for classifying what kind of stroke it is. This would be good in an ambulance. to check even before getting the patient to the hospital, which one is it? Is it ischemic or is it hemorrhage? So we made this kind of simulated phantoms. This is a healthy two-dimensional patient. This patient has an ischemic stroke, and this one has bleeding in the brain. So the goal here is to use a novel way to use the CGO solutions. As you can see here, what I'm showing you is a little bit like X-ray tomography, although there are no X-rays involved. This is virtual hybrid edge detection I'm using. We have virtual X-rays, and we have this kind of a profile where you see when we come here, this bump here indicates the skull, which is very resistive. Inside there is just a little structure, and then there is the other side of the skull also indicated by a big signal here. And then if there's ischemic stroke, we see this kind of signal, and with hemorrhage, we see this kind of signal. And we can look at these profiles from all directions we want, and these profiles can be computed from electrical impedance tomography data measured on the surface. So what I want to do is to explain you what information do these profiles contain and how to use them in machine learning as nonlinear features. So let me tell you a little bit about what this virtual hybrid edge detection is. This work is done with Alan Greenleaf, Matti Lassas, Matteo Santacesaria, and Günther Uhlmann. So now let's look at the complex geometric optics solutions that have a certain exponential behavior. So for that, let's take a point in R2 and a complex variable. It's kind of a complexified wave number. And I write it in this form where tau is a real number and theta is a unitary complex number. Then we take such vectors in C2. So these are complex 2 vectors. And there we can, if we compute this, if we use the complex notation for the planar point, so this multiplication actually equals x dot eta, where eta is this vector. So we are looking at solutions of the conductivity equation with such exponential behavior. So there's the leading order behavior exponential of this type, and there's a W, which is a deviation from the pure exponential. So let's see what equation this W satisfies. So now we have this form for U. So let's put this into the conductivity equation here. We calculate, and we can take away the exponential. So we see that W, the deviation from pure exponential, satisfies this second order equation. So we have the Laplace. Then we have a complex valued first order term here. So this eta is a complex vector. And then we have also some other terms like this. And now we can do this new trick that leads to this VHED approach. We take a one-dimensional Fourier transform in the real tau variable in the polar representation of the complex wave number k. So we Fourier transform with respect to tau, and we call the resulting variable t pseudo time for reasons that hopefully become apparent in a minute. So now this was the equation for W. So we Fourier transform this one, so we get another equation for W hat. And here the multiplication by tau here becomes a derivative in t. And now we can analyze this partial differential operator along the lines shown by Duistermaat and Hermander, because this is a complex principal type operator. And what follows from this one is that for real principal type operators, for example, for the wave equation, we have a one-dimensional ray along which singularities propagate. But what's interesting about these complex principal type operators is that singularities propagate along two-dimensional leaves. So they look something like this, how singularities are propagating. And I'll show you an example in a minute. But first, let me go a bit more technical with a specific type of CGO solutions, namely the ones based on the Beltrami equation, introduced by Astala and Päivärinta in 2006. So we define a coefficient mu from the conductivity like this, and then we look at functions f with real and imaginary part that satisfy this Beltrami equation. So you see this mu is here as a multiplier, and then we have the z bar and z operators on both sides. So this is the Beltrami equation, and then it so happens that the real part of f satisfies the conductivity equation, and the imaginary part satisfies the conductivity equation, but with 1 over our conductivity. So this f is encoding a lot of information about the conductivity equation, although it's a solution of the Beltrami equation. So these CGO solutions have such a form. So we have two of them, one for sigma and the other one for 1 over sigma with plus and minus. So we have each of the ikz, where ikz is really the complex multiplication like this. So we have, it's 1 plus a deviation. So these deviations are the interesting nonlinear features here. Oh, this is a quick history of these methods. I'll just go quickly on that. So now if you look at the one-dimensional Fourier transform trick, what happens is that we take the k as before. So the k is a complex parameter, and we Fourier transform over tau, and we get the t, which is the pseudo time. So how does this look like now when we take an example? Let me also mention that in here we have the z, which is a point on the boundary. We are restricting z on the boundary of the domain. We can also integrate over the unit circle, kind of collect together all of the CGO solution information all over the boundary with this kind of operator t plus and minus. And now Rashmi Murthy was kind enough to compute a few examples. How do these functions encode information about jumps? So this is the virtual hybrid edge detection. There are hybrid because it's kind of X-rays and EIT, but virtual because X-rays do not really exist here. So now if we only look at the Fourier transform omega plus, we see that the jumps in this simple digital phantom show up as some kind of signals, but this signal is much stronger than this one because our z point is here. So which is more far away, it's weaker, and there's a weird wiggle in the middle. It turns out when we subtract these plus and minus guys, the nonlinear artifact in the middle is gone, but still we have the situation that the boundary closer to z is much more pronounced than the boundary far away from z. But when we integrate over all z values at the boundary, we get this kind of symmetric information about jumps in the conductivity. So now I want to say a little bit about what information we think is there, or how can we analyze the information content of these functions. So this is also, we have to take a closer look at the construction of these CGO solutions. So we have these few functions we have to define, and this operator that contains the solid Cauchy transform and the Berling transform, and then pointwise multiplication by a couple of functions like this. So this is kind of a little modification of the original construction by Astala and Päivärinta. This was done by Huhtanen and Perämäki with numerical efficiency in mind. But it turned out that this rewriting of the construction is also useful for our analysis of information content. Namely, we can write these omega functions as an infinite series like this, which we can define in a recursive manner, starting with just the alpha, well, alpha bar and minus sign, and then we start applying the A operator to the conjugate, and also from this un we get omega n. And now these terms we can analyze, especially the first term, omega 1. We can exactly understand how does that code the singularities of mu, which is very close to the conductivity already. So first of all, let me show you how these terms, the first term looks like. So if we take this kind of very simple conductivity as a jump along a circle, we have this kind of picture of propagation of singularities. I will cut this picture along a plane, which you see here. So the singularities travel like this. During the origin, there is always a singularity propagation line or plane with slope 2. And when this one hits the jump in the conductivity, so the jump is at radius 0.2. So we have this jump and this jump. So when this one hits here, it creates a horizontal singularity that we can see in the first scattering series term. So we have very strong signals from the discontinuities, and the higher order terms are smaller, which is good because then we can ignore them. And then we have second order scattering because these horizontal ones again hit the conductivity jump and create another slanted line, which again hits here and creates another second order effect, which has no effect in the first order term, but it does have a very little effect here. We can't even see, but there is a little bit. So this way we can see that the most dominant term is the first one. And for the first one, we can prove a filtered back projection formula that we can actually get mu back if we knew T1, the first order operator applied to mu. Then we apply the adjoint, which is kind of a back projection operator, and then a filter. So if you compare what happens with the radon transform in X-ray tomography, you first measure the radon transform, the line integrals of F, then you apply back projection and you filter and you get F back. So this is completely analogous. If we had here, this one we don't have in practice, we have to involve the full series here, but the higher order terms are smaller. So we are almost correct with this one even in practice. But mathematically, if we had this operator, we will have this formula where this is like the radon transform. This one is like the back projection, and this is the filter. Although this is a smoothing filter, whereas in the usual FBP, it's a differentiating filter. Just to quite remind you what this formula is doing. If we measure X-ray data of two disks like this, we can recover the disks by using back projection like this, and then we do the filter. So we go to the Fourier side, we multiply by C. Calderón appears also here. He seems to be everywhere. And then we do the inverse transform, so we get the original. So the structure of our new formula is the same. So we can also do a recovery of the conductivity from our VHED profiles. Although there is a catch, which I will explain now next, because we are dealing with much more ill-posed problem than X-ray tomography. EIT is exponentially ill-posed, so we are not getting away so easily as using a radon transform type technique. noise will play some tricks on us. So let me comment on the noise and then show how we can use machine learning. So this part is very recent joint work with Juan Pablo Agnelli, Ainur Chell, Matti Lassas, Rashmi Murthy, and Matteo Santacesario. Okay, so this is what we hope for, but I have to tell you that I computed these pictures with very highly unrealistic interval in the complex frequency domain. I used a cutoff radius of 60, whereas in practical EIT you can use cutoff radii of like 4.5 maybe. If you have very low noise device, maybe you can push it to 5, but 60 is really a very mathematical construction, not very practical. But to see how these look like. Okay, so if we had those very unrealistic VHED profiles available, I think we can see with confidence, is it hemorrhage or is it ischemic? But this happens when we have noise. We have to heavily window our one-dimensional Fourier transform because of noise. So from these very detailed functions we see here, we go to these much less detailed ones. So what I'm showing here, these two are, well, these functions. So this is the t plus operator minus t minus operator applied to these Fourier transform guys. So this is the formula for these functions. Red is for hemorrhage, blue is for ischemic. And what is this omega hat plus a, sub a? Sub a means that we have to use a window here that essentially cuts this integration within the limits of noise robust information. Let me try to be even more clear with this noise robust interval. So what you see here, this is now in tau space before the Fourier transform. Like if I go back here, remember this Fourier transform is taken over the tau variable, and we end up with the t variable. And then we plot something that shows the location of singularities. In the tau space, before this Fourier transform is taken, we can analyze the effect of noise. Remember, in the D-bar method, we had a stable disk, and outside the stable disk, there was just numerical garbage. Here, it's exactly the same thing. When we look at these omega plus functions as the function of tau, so I now fixed the direction or the argument of the complex wave number k, and I fixed the z point at the boundary. So the only thing moving here is tau, which is the kind of polar component of the complex wave number. So now what I did is I computed these function values from a simulated Dirichlet-Neumann map, and I added noise. So here I added low noise, but with many realizations of noise, and for each realization I computed this function. So you see that the effect of noise kicks in only after tau is outside some interval, exactly like this stable disk in the D-bar method. And now when we have more noise, this interval where these noisy computations all agree to reasonable extent, the interval is more narrow. So this shows how badly we have to window the Fourier transform. So with more noise, we have to squeeze our Fourier windowing. Okay, and at this point, for this to be useful for the stroke classification, we need to ask, can we use these VHED profiles? I mean, not these, which are quite clear, but these that where the information is much more blurred. But we understand geometrically very well what is in these functions. We know that jumps in conductivity show up as singularities here, propagated along virtual X-rays whose direction we know. And after the singularities pop up in these profiles, the profiles are heavily convolved because we have the window on the Fourier side. So this is something this is not a black box at all. This is a noise robust computation, which we understand geometrically very well. So the point is that now we have done part of the inverse problem with analytically understood and noise robust methods, and then we apply machine learning. So then it's not a black box algorithm, it's kind of a gray box algorithm. So the first part is well understood and known, and then we apply some machine learning, which we cannot fully analyze what it's doing. Okay, so what we did in this study, we simulated a lot of thousands of examples like this, where there is either an ischemic or hemorrhagic simulated stroke on the right hemisphere. We know in practice on which side the stroke is, because we can ask the patient to lift both hands, and they can usually lift only one hand. So then we know the problem is on this side because it's the opposite from the hand that doesn't work properly. So without loss of generality, we assume we know on which side the problem is. So we simulate a lot of disc-shaped strokes, and we test the results with a more general set, namely with ellipses, and also with some irregular shapes, and even multiple inclusions like this. Thanks to the observant referee, we added these multiple cases, which is quite interesting. So many thanks to this anonymous referee who suggested this addition to the paper. Okay, so we compare two approaches. Either we compute the Dirichlet-Neumann matrix, which we do in the simulated case. We do it like this. We first compute the Neumann to Dirichlet matrix. We apply a Neumann condition at the boundary. One by one, these Fourier modes. We apply the Neumann to Dirichlet map by using finite elements. And then we calculate the inner products with other Fourier basis functions. So we get a matrix like this for each of those simulated phantoms I showed you. And then we invert the ND matrix and add some zeros in the middle row and column. So then we actually end up with an approximation to the DN operator. So we compare two things. Machine learning classification of the type of stroke with such a matrix as input. So this is a black box. Can the machine learning overcome the ill-posedness and understand the EIT data as it is and classify from what kind of stroke it's coming from? And then the other approach is we use these matrices to calculate those heavily convolved VHED profiles, and we give them to the machine learning as nonlinear features first extracted from the data before the learning. So which one is better? Do we get better results by this gray box approach, first drawing the nonlinear features and only then learning? Because this step will also overcome the ill-posedness. All right, so first we tried convolutional neural networks, and this is the architecture for the DN matrix input, and the output layer gives the classification to either ischemic or hemorrhage. This is the convolutional neural network architecture for VHED profile input. So we have a few layers, 4 convolutions, some max pooling and ReLUs in between, and finally one fully connected layer there. And as the result, we get so we also put in varying levels of noise to the DN map. So you can see that the accuracy in learning for irregular inclusions is quite a lot better with all noise levels when we first draw the robust nonlinear features and learn from them. Also now when we generalize to the two-component case, which is already quite different than the training set. So we trained with just one disk somewhere, and now we are testing with several inclusions that are not necessarily disks. So the quality of the DN matrix learning drops dramatically. So this is already completely unacceptable level of classification, because if the patient has hemorrhage instead of ischemic stroke, but the classification says it's ischemic, then a blood thinning medication is administered and the patient is really in mortal danger in that. So hemorrhage patients shouldn't ever get blood thinning medication. The CNNs from nonlinear features is better, but this is also not really good enough for the ambulance use. Although, like Rashmi informed me, she is experimenting with other CNN architectures, and she's getting better and better results all the time with different architectures. We also tried fully connected neural networks of this form. And there we actually got very nice results. For these irregular shape cases, we have very, very high accuracy. So we tested with 1,000, so all of them were correct in these cases. And then with noise, we had some trouble. Also, the DN matrix learning is almost on a medically acceptable level. And then when we have multiple inclusions, we see that the quality of the DN matrix learning again dramatically drops down. So this is again completely unacceptable. Whereas the nonlinear feature learning is doing still quite well. And now this is very curious. With small noise, we have worse results than with higher noise. So this is a bit curious. Our working hypothesis is that adding noise is a little bit regularizing this learning and leading to better generalization. But this is something we will take a further look in later research. Our paper with these results is already in arXiv, and it's appearing soon in inverse problems. Okay, so we think that it really pays off to first use traditional regularized inversion math to draw nonlinear features and learn from them. And also in these experiments, we found that fully connected neural networks perform better than CNNs. With further studies with more complicated situations, maybe fully connected ones are too heavy computationally, we'll see, and then maybe we have to use RNNs or something else. And our next steps will be going to 3D simulated and 3D measured data and see whether our 2D model can generalize into that kind of data. So thank you very much for your attention.
Thanks a lot, Samuli. Thank you. So people can post their questions either in the Q&A box or in the chat, or I give you a third option. You can also raise your hand and Fadil will unmute you. And you can ask your question in person, personally. So while people are thinking or typing, Samuli, what so the fully connected networks, as you said, they will pose at some point a computational hurdle for you in a way, right?
Maybe so. It really depends on how much, how many VHED profiles we feed in, and we kind of have the suspicion that maybe when we go to the situation that we measure the data from an actual 3D object, for example, a band of electrodes around the head. So then the data comes from a 3D object, and we are still analyzing it with a 2D phantom trained network. This maybe, well, maybe it doesn't work at all, or maybe it works, but we suspect maybe we have to feed in more VHED profiles than we do now. And then the dimensions of the network may blow up, but yeah, we don't know yet.
Yeah, okay, good. We have a Q&A here. Ah, okay. One of the participants said, "Thank you very much."
Oh, you're welcome.
Okay. So at which point do you think the combining the domain knowledge with the neural network was what's the most crucial component in bringing your vast experience in EIT together with machine learning in this? In this stroke prediction, in the sense that what's the important component that maybe someone who doesn't know much about EIT could not have done?
I think it's the overcoming the ill-posedness. I think the trick here is to first draw out information that we know is robust and which we understand geometrically. What is the information contained in the robust ones, and leave out the noise sensitive ones, and then go from there. Because in the original measurement, the DN matrices, all of the information, the unstable and the stable one, they have been intertwined together in a very nonlinear way in the DN matrix. And this whole complex geometric optics solutions business unravels this complicated knot and divides the information into stable and unstable. I think this is the crucial point. Yeah. Especially with this kind of very ill-posed problem. And I think this thinking will generalize to other problems than EIT. If always one first draws out some, be it like inverse scattering, if you think about, let's say, the factorization method, if you draw out a regularized factorization map, you get, and then you learn from that one, because you still have, for example, the problem of choosing the level with the function you draw from the factorization method, which level is the right one to cut it. So maybe that's much easier to learn than to learn the information about the scatterer from the raw data.
Yeah, so it's really where you insert the learning component.
I think so, yes.
So I think I think Eric has a question for you as well, Samu.
Yes, Samuli. Hi. Let me put my video back. There we go. Yes. When you detect hemorrhagic stroke, the conductivity changes because there is an accumulation of blood, right?
Yes.
And that could create a higher conductive medium, in a way, inside the brain. So what is the physical or physiological difference with an ischemic stroke then?
Well, there is much less blood in that area, and I think the neural cells, they use up all the oxygen that is there, and it gets used up. So, but we don't know for sure, because these are really hard things to measure. And I think actually the conductivity values that are in the literature, I'm not sure how reliable they really are, because the doctors tell us that you should really measure this from living brain with this particular problem in it, right? Because after death or other kind of intervening, it will immediately change. So it's kind of hard to know what is there. So it would be good to have some more experimental understanding of the actual conductivity.
So you think it's just a matter of the concentration, or it would be like comparing a mild change of conductivity to a bigger change of conductivity?
Maybe, but you know, the cells, for example, also the cells will suffer in both cases. There will be swelling of the cells, and also, I mean, in ischemic, when they are deprived of nutrition, the cells will also, they are suffering very much, and they start to die at some point. So this certainly affects the the tissue in some way, but I'm afraid this is not very deeply understood. Yeah, unfortunately. So that may be another reason why maybe the machine learning is good. Even if we don't understand so properly what's going on there, maybe the machine learning will be able to pick it up from the, yeah. It's a bit unfortunate to think like that, but maybe it's what we have to go with.
Well, thanks for the talk anyway. It was great.
Thank you.
So any more questions? There is another thanks for a very interesting talk, Samuli.
Sure. Thank you. I'm glad you liked it.
I don't see more questions. So yeah, thanks a lot. I mean, this was super interesting, Samuli, and as always, very entertaining.
Oh, good, good.
This last picture is totally unrelated to the talk, right?
It is, yeah. I'm just so very proud of these red things on the bottom left, because a couple of years ago, I like weird animals and weird organisms for some reason as a hobby, just aside inverse problems. This is just a free time hobby. So I found out first that slime molds are really strange organisms. They are kind of related to amoeba. They are not plants or animals. They are really far away from anything regular. And then I realized that you can find them easily almost everywhere, especially in the fall. So then I started to photograph them, and within a couple of weeks of this slime mold hobby, I stumbled upon these red ones, and it turned out that this was the first find of these slime molds in Finland.
Wow.
They had been found in Sweden, but I, as a total amateur and beginner, was able to find a new species for Finland. So I'm so immensely proud of this chance encounter that I include this picture in my talks.
Following Humboldt's
indeed.
footsteps. Yeah.
And then I always think if this math stuff gets just too difficult, then moving to biology should be fine, because it seems to be so easy. No, sorry, just kidding.
Yeah, no, that's very nice. Thanks a lot. There is another many thanks from Ursula Spivak as well. Yeah, so you have lots of positive feedback for the talk. Thank you, Samuli. It was really, really interesting. So if there are no more questions, I hope I'm not overlooking anything. Then thank you very much again, Samuli. And we reconvene again next week.
Excellent. Thanks for organizing. This is such a good seminar series, especially in these troubled times. It's good to have this way of sharing ideas. It's great.
I agree. Yeah. Thank you. Thanks for contributing.
Thanks.
Bye-bye.
Bye.